Well, all right. So I welcome you again. And as we were discussing the bonding theories in transition metal complexes, and in the previous couple of classes, we had a good discussion on the introductory theories like Werner's work, and then the VBT, the Valence Bond Model, to explain the properties of transition metal complexes. And now we are discussing the crystal field theory. Okay, in fact, we had a good discussion on how the splitting takes place under different crystal field, different geometries, how the crystal field splitting takes place, how the d orbital splitting takes place. Okay, so now after we have uh, a good discussion on how the splitting takes place, now the next course of action is that we first understand that how this splitting is affected, what are the factors that are affecting the crystal field splitting, and then we will try to explain some of the properties of transition metal complexes using crystal field theory. As I told you that in case of an octahedral crystal field, right? So the two energy gap that are formed are like T2G having the dxz, dyz, and dxy orbital below the barycenter minus 0.4 delta O below the barycenter, and EG orbital, that is dx square minus y square and dz square, they are plus 0.6 delta O above the barycenter. Okay. So now this delta O, how do you measure it? Okay. I think we slightly had a discussion on this also, that in order to measure this gap, so-called the gap between the T2G and EG energy levels, we make use of spectrophotometer, UV visible spectrophotometer, because this gap corresponds to the electronic transitions, and that can be measured in the using the UV visible spectrophotometry. We took the example of titanium hexa aquo 3 plus. It's a purple color. It's the compound has a purple in color. If you make a solution of it, okay, and simply it is a D1 system, means having only one unpaired electron, only one electron in the D subshell, right? So when the splitting takes place, it's an octahedral system. A T2G and EG energy levels will be created. So the configuration is T2G1, EG0. When you are exciting it, you are forming a T2G0 and EG1. That means the single electron present in the T2G orbitals is now excited to the EG level, right? And that is why the energy absorption takes place. Absorption takes place, and that is around 520 nanometer, right? 520 nanometer. So, which will be corresponding to about 243 kilojoules per mole. So you know that this energy level is corresponding with the electronic transitions. Well, so you can see the ground state is having the single electron in the T2G set, and then it with the application of energy, it goes to the EG level, right? So that is how basically this is happening, right? So in this case, the titanium hexa 3 plus, which is purple in color, you can explain that because the energy of a particular wavelength, that is 520 nanometer, is being absorbed by this particular complex, and the corresponding color that will be seen. Okay, as I told you earlier also. Anyway, so in this way, the absorption spectra to some extent is explained for the transition metal complexes. Also, it is a much better explanation for the color property, the color of the transition metal complexes compared to the earlier theories. Okay, so as I told you that we need a discussion on how this delta O, that means the gap between the T2G and EG, is varying, and what are the factors affecting it. Okay, as I told you in the last class also, that nature of the ligand is important. Okay. In fact, by doing this method, using this method of making a complex and measuring its electronic spectra, then checking at what wavelength it is causing this shift, right? You are getting an idea of the delta O. So you can do this. You can make a series of transition metal complexes, okay? And here you will have a good idea that which ligand is causing more splitting and which ligands are causing less less splitting, right? And based on that, you can create a series of the ligands. Like for example, that iodide, bromide, basically halogens are on this left hand side in this spectrochemical series, and the ligands like ammonia, ethylene diamine, pyridyl, phenanthroline, right? They are on like in the left hand side, that means on the stronger field side, while the ligands like cyanide and carbon monoxide are very strong field ligands because they cause a large splitting of d orbitals. Okay, the charge on the metal ion. As the charge will increase, let's say a plus 2 oxidation state and compared to a plus 3 oxidation state will have more splitting. A plus 3 oxidation state will have more splitting than plus 2 oxidation state just because it can attract the ligands. Because ligands are having, the empty space, or the negatively charged ligands will be having more attraction with a highly positive charge, right? So in that case, there is a better interaction between the metal and ligands, and that is why more splitting you will be observing. The third case is that if the ligand, if the metals is a 3D, 4D, or 5D element. So in a 5D element has more splitting than 4D, and a 4D has more splitting than 3D. Okay, this is because the size of the 4D and 5D orbitals is huge. Not only the pairing of the spin is very easy in the larger orbitals because of the lot less Coulombic repulsion, but also because their size of the orbitals is huge, they can have a much effective, better orbital overlap with the ligand orbitals. Okay, so both the factors suggest that a 4D or 5D elements are mostly they are low spin complexes. It's very easy. It's very easy to cause a huge splitting over here, and very easy to pair up the electrons into the lower energy levels. Okay, so that is important. This data is quite good in for your understanding of like to get in like quantitative idea that how generally these splittings are. Okay, like chromium hexafluoro 2 minus, right? It's an octahedral. All of them are octahedral except this example, the entry of 9, which is a tetrahedral example, except that all are octahedral. In fact, octahedral geometry is the most common geometry among most of the transition metal complexes that we come across. So chromium hexafluoride is having 22,000 centimeter inverse. Okay. So chromium here is in, if you see, the oxidation state of chromium is plus 4, right? CrF63 minus, chromium here is plus 3 oxidation state. So plus 3 oxidation state, you can see is having only 15,000, right? Metal is same, ligand is same, geometry is same, delta O is not same because the oxidation state is not same. A higher positive charge will attract ligands more closer, better interaction, so more repulsion between the electrons present on the metal and ligands, so more separation will be there between the T2G and EG levels, right? Comparatively, a lower oxidation state will not have the same effect. So you can see the chromium plus 3 oxidation state is having less splitting than a chromium in plus 4 oxidation state. Clear? Chromium ethylene diamine thrice, right? En3, 3 plus. Chromium in 3 plus. But this is 22,300, where even in fact larger than the chromium 4 plus for here. What is the region over here? Okay, you must be wondering. The region is ligand over here. If you notice carefully, although the oxidation state and the entry number 2 and 3 are same, right? They are same. Chromium 3 plus, chromium 3 plus. However, the ligand, ethylene diamine, if you look at the spectrochemical series, right, while the fluoride is a weak field ligand, it's on the much on the left hand side, Where the En is on the right hand side, you can see En is already, in fact, it is stronger than pyridine or ammonia, right? So it's a much stronger ligand field compared to a fluoride ligand. That's why En will cause a lot more splitting than the fluoride ligand. CrCN63 minus, again chromium in 3 plus oxidation state. Let's see what happens over here. Octahedral, of course, 26,600, even higher than chromium En3. Again, you can see the same oxidation state, ligand is different. You go back to your spectrochemical series, see where the position of cyanide. Oh, cyanide is very strong field ligand, almost, uh, strongest in the series, just below carbon monoxide. It's very strong field ligand, right? So that's why the CrCN63 minus is having 26,600. Okay, so you see that how much is the effect of the ligand. It's much more than in the what oxidation state has to play, right? Like +4 oxidation state of chromium is having lot less than the chromium CN63 plus, which is chromium is 3 plus oxidation state, but is still having a larger splitting because of the strongest, one of the strongest ligand, that is cyanide, present over here. Let's take more example. Iron hexide for 3 plus. So iron is in, water is in neutral ligand. So iron is in 3 plus oxidation state. Octahedral geometry. Iron hexide for water, we know, if you look at here, water is somewhere over here in between. So water is generally considered as an intermediate or weak side ligand, basically. So it has only 14,000 centimeter inverse, right? All these are experimental data already. Okay, around 14,000 centimeter inverse. And iron CN63 minus. So again, iron, Cn being a negatively charged ligand. So effective oxidation state of iron is +3 over here. How much? 35,000. See how much difference. Both both the entry 5 and 6, they are having same oxidation state of iron, that is +3. However, one case 14,000, another case 35,000, which is very high. 35,000 is very high compared to 14,000. It is again because cyanide is a much stronger field ligand than the water. Right. Now you see example of cobalt. Cobalt hexamine 3 plus 22,870. Okay. Sorry, cobalt, yeah, cobalt hexamine 3 plus 22,870. Cobalt hexamine 2 plus octahedral only 10,200. What is the reason? Both same ligand, same metal, oxidation state is different. Cobalt here is in 2 plus oxidation state. In fact, stabilizing a cobalt hexamine complex is very difficult because it would like to go for a +3 oxidation state because ligand is stronger side over here. Because this is more the splitting, okay, more is the stability also. That which we will see later. Okay, so 22,870 is very high compared to the +2 oxidation state of cobalt and only 10,200 centimeter. It's good to go through this data. You get a real picture of what is happening in various metal complexes. Cobalt tetramine 2 plus. Again, cobalt is in 2 plus oxidation state because ammonia is a neutral ligand. So here the geometry is tetrahedral and it is only 5,900, almost half of this cobalt hexamine octahedral case. Remember, we also discussed that octahedral and tetrahedral splitting is only 4 by 9 of octahedral, right? So if you just carry out this calculation, I'm very sure it will be very close to 4 by 9, right? 5,900 divided by 10,200 will be close to a 4 by 9 factor. Okay, so as I told you that time also that all these data, all these theories are basically either the data has to be supported by the theory, right? So that 4 by 9 theory is supported by the data. That's why everybody believes it. Okay. Iridium hexamine 3 plus octahedral 41,000, highest I think among all these examples. Why? I told you that iridium, okay, so cobalt and rhodium and iridium are in the same family. So because I told you that a 4D and 5D elements will be having much more effective orbital overlap as well as better interaction with the ligands, right? Pairing is very easy because of the large size of the orbitals and because of all those factors, okay, you see the iridium is having a 5D orbital, right? So no problem in pairing of the electron. So 41,200, you can explain why it is so high. Although cobalt, iridium, rhodium, they are in the same family, but see cobalt with ammonia, okay, octahedral geometry, 10,000. Iridium, same ligand, same geometry, 41,000, 4 times more. Okay. If you consider all these factors, the nature of the ligands, the charge on the metal ions, whether the metal is 3D, 4D, or 5D elements, you will be able to explain any of this data. All right. Some more examples are over here. Chromium Cl6, 13,000. Chromium 3 plus. Chromium hexaco 3 plus is 17,000. What does it suggest you? It suggests that water is slightly stronger field ligand than the chloride. Let us check in the spectrochemical series. Yes. So you can see chloride is in the much low, lower or weaker field side compared to water. Water is almost in between, right? So all these things can easily be explained if you consider these three factors: the ligand, the oxidation state, and also whether it is 4D, 5D, or 3D, which metal we are talking about. Chromium hexamine, ammonia is a stronger field ligand compared to water and chloride. So you can see that the splitting is higher in this case. Cyanide is even stronger, and you can see that it is 26,000 highest among all these examples, because cyanide is the strongest field ligand in all these four. Cyanide is stronger than ammonia, stronger than water, and stronger than chloride. Okay. So if anybody gives you these four complexes and do not give you the data and ask you that you arrange these four in terms of either decreasing delta O or increasing delta O, you should be able to do it by considering just the effect of ligand, the spectrochemical series. Okay, in fact, this type of questions are very common in many competitive exams. Cobalt, hexamine 3 plus, rhodium, iridium, right? I told you that cobalt, rhodium, iridium are in the same family. It's a perfect example to discuss. Cobalt, RHIR, same oxidation state, same ligand, same geometry, everything same. Metal is different. Cobalt 24,800, rhodium 34,000, iridium 41,000. Okay, 3D, 4D, 5D. I told you when the orbital size is increasing, okay, the two factors, better orbital overlap and pairing of the electrons is very easy. So that's why this is very high. Okay, what is this pairing? Pairing I am talking about pairing of electrons. Okay, so if you look at the D1 case, right? D1 case, only thing is this electron will have to occupy a T2g orbital. Either of the three degenerate T2g orbitals will be occupying. And if you keep varying the ligands, only thing is the distance between this or this delta O will vary. Position of the electron will not vary. It will remain. Whether weak field or strong field, it will remain into the T2g set. No change in the position of the electron. Only the gap between the T2g and EG, that is something that is going to be changing. Okay, D2 system same, D3 system also same. Alright, D1 to D2, D3, there is no effect in terms of number of unpaired electron. There is same, it is same all the cases. However, if it is D4 case, if you have a stronger field ligand, then you might have all the four electrons present in the T2g set. Okay, if you have weak field ligand, three electrons will occupy T2g, one electron will occupy this orbital in the EG set. This is called high spin nature. This is called low spin nature. In the strong field, if this gap, so what is happening over here? You have to pair up. You have to force the pairing in this orbital. So if this gap is much more than the pairing energy, in that case, the pairing will be easily taking place. However, the gap is less than the pairing energy. In that case, it is not effective. It is not wise for electrons to get paired up. They will be easily staying in the high spin form, right? So number of unpaired electrons will be high, magnetic moment will be high, and if the stronger field ligand is there, number of unpaired electron will be less, and the magnetic moment will also be low, right? So that is the thing basically, right? In fact, this is not the case of D4. If you take from D4, D5, D6, D7, this high spin, low spin case will always be there, depending on what kind of ligand and what is the ligand field that is there. If it is a strong field ligand that can cause more splitting than the pairing energy, you will end up in a low spin formation, low spin complex formation. However, if the gap between the T2G-EG, the delta O, is less than the pairing energy, in that case, you are going to have, a low high spin case. Okay, this is a very important slide that you can see over here. D1, D2, D3, always high spin, no question of pairing of the electron. Okay, D8, D9, D10, again no question of pairing of the electron because T2 set is completely full, or you have to only fill up the orbitals over here. All right. So only the D4, D5, D6, D7 you have to pay attention. What kind of ligand system is there? Or if you have the magnetic properties already knowing, you can easily predict whether it is a low spin or high spin. If the ligand is a stronger field ligand or it is a weak field ligand, you can easily tell. So see, suddenly just by considering the d orbital splitting, we are able to know so much about the transition metal complexes, right? In the previous few slides, we were able to explain the spectra, the color of the transition metal complexes. Now we can see the magnetic properties have a direct correlation with the number of unpaired electrons, the magnetic moment we can easily predict, right? If it is depending on what is the electronic configuration, what kind of ligands are there, what is the oxidation state, whether a metal is 3D, 4D, or 5D, what is the geometry, all these factors if you consider, you will be in a very good position to explain the properties of transition metal, the particular transition metal complex. All right. Now moving on, like just if you, I will reiterate these things. If you take this example of magnesium hexaco, it is magnesium 3 plus oxidation state, water being a weak field ligand, it will not cause enough splitting between T2G and EG. A fourth electron will take place orbital in the EG set. However, manganese hexacyanide 3 minus, manganese again manganese 3 plus oxidation state. Cyanide being a stronger field ligand, it will form a strong field complex. So it will cause enough splitting in the T2G and EG gap that will be much more than the pairing energy. So it's better to pair up the electron rather than exciting or putting electron in the EG set. That's why this will be a low spin complex, while manganese 3 plus is going to be a high spin complex. All right. I hope you are able to correlate this, like pairing energy and splitting between the T2G and DG delta O. If delta O is greater than the pairing energy, right, it will be low spin. If delta O is less than pairing energy, it will be a high spin. So you can predict down the state electronic configuration, magnetic properties, and color using all these things that we have just discussed over here. All right. So as I told you, I'll reiterate a few things like if there are more than one electrons, electron-electron interactions will take place. So especially if you would like to explain the spectral properties, we need to consider this. Okay, right now we are not considering the spectra. We are just thinking that in case of the D4 to D7 system, there are two possibilities always. Either you put the electrons in a T2G set and therefore pair the electrons, right? Low spin cases or strong field situation, or put the electrons in the EG set, which lies higher in energy, but electrons do not pair, high spin case or a weak field situation, right? Therefore, there are two important parameters to consider: the pairing energy and the EG-T2G splitting, the delta O or 10dq or crystal field splitting energy. All right. If, as I told you, both the high spin and low spin situation, it is possible to compute the, for both the high spin and low spin situation, it is both possible to compute the crystal field splitting energy, okay, or stabilization energy, okay. That is different, but we can compute crystal field stabilization energy, okay, for both the cases that we will see a little later. Before I go further, let me tell you a little more about the pairing energy. What are the factors that pairing energy depends on? So pairing energy depends mainly, there are two factors. So what is the P? Energy to cause pairing of electrons within a single orbital. That is called pairing energy. Okay. So one is Coulombic repulsion. If you are putting two electrons in the same orbital, there will be Coulombic repulsion. Both are having negative charge, right? So interelectronic repulsion between electrons occupying the same orbital decreases with the size of the orbital. 3D is having more repulsion than 4D. 4D is having more repulsion than a 5D orbital because of their sizes, right? It's just like if you have a bigger house, you can easily accommodate more people. If you have a smaller house, there will be more problems if you are occupying more people there. The repulsion will be there, right? That's why pairing energy is less in the 4D and 5D. That's why formation of the low spin complexes is higher in case of the 4D and 5D complexes compared to a 3D metal complex. Second is the loss of exchange energy. What is this exchange energy? Okay, it is basically energy when there are degenerate orbitals are there, and there are particles like in this case the electrons are there. Okay, the if the particles basically if they are having more room, they are having more room to go around. Okay, that system will be basically more stable. Okay, so loss of exchange energy based on the Hund's rule of pairing. Well, how do you find it out? Energy in exchange will be proportional to n into n minus 1. N is the number of parallel spins divided by 2. Right? So here how many parallel spins are there? You can see 1, 2, 3, 4, 5. There are 5 parallel spins, even although it is a D6 case, but parallel spins are 5. 10 is 5, so 5 into 5 minus 1 divided by 2 is 10. Okay, that is how you can just estimate the exchange energy. If you see D6 low spin, how many parallel spins are there? 1, 2, 3, okay, 4, 5, 6. Okay, so in this case, so 3 into 3 minus 1 by 2, 3 into 3 minus 1 by 2. So total will be 6. So see, D6 high spin is having much higher exchange energy compared to the low spin configuration, right? So which will not be allowed, right? So that you have to again put some more energy in order to cause a low spin nature, because you are losing the particles which can be exchanged. All right. While iron 2 with weak ligand sometimes the low spin complexes, and manganese 2 does not. Right. So you see over here iron 2 is having a D6 configuration. Manganese 2 have a D5 configuration. So manganese 2 has a higher exchange energy which it will not like to lose. So it will like to contain these 5 spins. However, it has less, right? If you find out here, it will be 4. In this case, it is 6. So in this case, the loss of exchange energy is less if you go for from a high spin to a low spin case. Okay, loss is only 4. However, in this case, loss is 6. All right. So that is why iron 2 can easily give a low spin cases. However, manganese 2 would not like to give the low spin cases. It would like to retain 5 unpaired electron, and that is why people say that a half-filled orbital is having extra stability. Why? People will say, somebody will ask you why manganese 2 is stable. You will say, sir, half-filled stability. It is fine, half-filled is okay, but why half-filled? This is the basis, that it will have more loss of exchange energy compared to, let's say, in a iron 2 system, which will have that loss in exchange energy is only 4. In case of manganese 2, the loss of exchange energy is close to 6. That's why it will like to retain a high spin configuration, the D5 configuration. All right. You can have a practical idea by looking at this data, right? A iron hexaco 2 plus D6 configuration, Fe 6 4 minus. Again, iron is in here also 2 plus oxidation state. Both are D6. Delta O is 10,000. Pairing energy here is 17,000. Both are iron, so both are 3D. So pairing energy, orbital size is same. So pairing energy has to be same almost, right? Unless there is a contraction in size because of the oxidation state or something, right? But here oxidation state is same, so pairing energy is expected to be same, right? However, the delta O is not. Delta O, cyanide is a much stronger field ligand compared to water. It is causing much more splitting, like 32,850, which is higher than the pairing energy. So a low spin complex will form in case of cyanide as a ligand. However, In case of water as a ligand, 10,400 delta O is less than the pairing energy, so a high spin complex will form. Understood? Similarly, you can see in case of cobalt, hexafluoro, 3 minus. So cobalt 3 plus, cobalt hexamine, again cobalt 3 plus. Both are T7 case. One is 13,000, right? Which is lower than the 21,000 that is the pairing energy. So it will result into a high spin case. While ammonia is a stronger field ligand than chloride. Delta O is 23,000 over here, which is higher than the 21,000 of pairing energy. So again resulting into a low spin case. So remember, cobalt hexamine is a low spin case. All right. By the way, this is a wrong representation over here. Cobalt hexamine 3 plus, with 3 plus charge here, not 3 minus. It is a mistake in the slide. Please note that it is a 3 plus charge. Okay. So I hope you are able to understand the pairing energy and the delta O connection. And what will happen if, let's say, the pairing energy and the delta O are almost identical, almost similar to each other? What will happen in that case? In that case, either a low spin complex or a high spin, either one can form. Sometimes, if you just alter the ligand's field slightly, a high spin will form or a low spin will form. Or if you just heat it up, if you just heat the complex, if from low spin it can go to a high spin. If you put some pressure, you can convert a high spin to a low spin. So it's very, they are very on the borderline case. Such complexes are called spin transition complex. D4 to D7 configuration can give you spin transition phenomena. So a high spin complex having large number of unpaired electron can go to a low spin complex having a less number of unpaired electron. Okay, a high spin can go to low spin because of the delta O and pairing energy are such that both are almost equal. Just by slightly changing the experimental condition, you might either get high spin or low spin. So in those cases, you will have to first carry out the magnetic property at different temperature or pressure, right? Then only you know whether it is a high spin or low spin. Otherwise, very difficult to tell. That's why these complexes are very interesting. Okay, many research groups are working on this type of system. All right, cobalt hexamine 22,870, rhodium, iridium. We already have discussed this example. I told you that 3D is having more repulsion in 4D than 5D. So it's easy to pair up the electrons in 4D and 5D. The splitting is higher. It's also higher because the orbital overlap with the 4D and 5D is stronger than the 3D case. Okay, so delta O varies irregularly along the period. Chromium, iron, cobalt, there is no connection almost, right? So chromium is 17,000, iron is 14,000, cobalt is 20,760, depending on how good a ligand and metal is interacting. Okay, if that is matching better, you will see a more splitting. If that, I hope you remember your simple hard and soft acid-base principles, right? If more hard interaction is there, more splitting, more soft interaction, more splitting, right? If a hard and soft are mixing up, then you have a confusion, right? So that's why cobalt and water is having more splitting than the chromium and water. All right, chromium 3 plus is, I guess, more harder compared to a compared to water is a ligand. Okay, and like that. Okay, all right. So if we have understood by now that how this splitting of the T2G and EG gap of the octahedral case or tetrahedral case or any other geometry basically, what are the factors that will be affecting it? All right. If we have discussed various examples of such cases, which can easily we can explain by talking about those factors, three factors that I told you, and that the effect of the ligands, the oxidation state, and nature of the orbitals, so that is 3D, 4D, or 5D. Okay, if you consider these factors, you will be able to explain the splitting, magnetic property, pairing, whether pairing will take place or not, a low spin will form or a high spin will form. All these things you can tell. The next thing that comes actually is the stability. Is the stability of the system. So we will take about 10 minutes on this topic. CFSE, crystal field stabilization energy. What is this? The energy difference between the distribution of electron in a particular crystal field and that for all electrons in a hypothetical spherical or uniform field level is called the crystal field stabilization energy. This is basically a measure of the net energy of occupation of the d orbitals related to the mean energy, that is very center. Like over here, this is the very center. If electrons are not occupying here, they are going over here. That means it is more stable. They are going to a low energy level. Or if the electrons are going there, in that case, they are going higher than the very center, so it is destabilization. All right. We told you that this is minus 0.4. T2G sat is minus 0.4 delta or below. So if electron is occupying here, we can say that a compound is more stable by minus 0.4 delta. All right. Or if a compound is occupying, if a electron is occupying dx square minus y square or dz square, it is destabilized by 0.6 delta, right? So can we just looking at how many electrons are occupying T2G, how many electrons are occupying EG? Can we calculate this by multiplying minus 0.4 and 0 plus 0.6? Whatever value will come, that is our CFSE, crystal field stabilization energy. Please differentiate it from crystal field splitting energy. Splitting energy is just the measuring this gap, the energy gap between this and this level. However, this will be a calculation of that if electron is not occupying here, the very center, electron is occupying a T2G set or DG set, then how much is the net stabilization? It is sometimes also referred to as how much energy is released when a metal complex is formed. Okay, that is also can be correlated with the crystal field stabilization energy. All right. You see over here, this is D1 case. D1 case will always the CFSE, crystal field stabilization energy, is always minus 0.4 delta. See, crystal field splitting with every ligand, it will vary. It will vary always. Crystal field splitting energy will vary. Crystal field stabilization energy will always remain minus 0.4. If it is D2 system, it will always be minus 0.8 because there are two electrons, 2 into minus 0.4. So minus 0.4, 0.8 delta O. D3 case, always minus 1.2 delta O because there are 3 electrons, so 3 into minus 0.4, right? So we can see that a D3 system having a more CFSE, more negative CFSE, so D3 system is going to be more stable compared to a D2, compared to a D1 system. Wherever there you see a more crystal field stabilization energy, okay, you can always correlate it with the stability of the complex. The best way to calculate CFSE is, this method, which I'm going to tell you. The crystal field stabilization energy is defined as the energy of the electron configuration in the ligand field minus the energy of the electronic configuration in the isotropic field. Isotropic field is very center, right? When no splitting has taken place. That is the isotropic field. So CFS is equal to delta E energy gap in between E ligand field minus E isotropic field. So CFSE will depend on multiple factors like geometry, number of the electron, spin pairing energy, ligand character. Right? Remember spectrochemical synergy. Let's take example. Take the example of D7 high spin case. D7, let's say there is no splitting, isotropic field, you feel the electrons like this. All electrons are having here, the level is having 0. So 7 electrons are there. So energy in the isotropic field will be 7 into 0. 7 electrons, 0 energy level. So 7 into 0 plus 2p. What is 2p? That is, there are two orbitals having paired spin. Two orbitals having paired spin. So it is 2p. Okay, please always consider this. This will give you the most correct answer of CFSE. So effectively, energy in the isotropic field is just 7 into 0 is 0 plus 2p on 2p. Energy in, let's say, octahedral field. Now the splitting has taken place. 5 electrons are taking T2G set and 2 are going in the EG set. So minus 0.4 into 5, right? And plus 0.6 into 2. And again, there are two electrons with two orbitals having paired spin, so plus 2p. So 5 into minus 2.2 by 5 or minus 0.4 plus 2 into 3 by 5 delta O plus 2p. So this energy is coming minus 4 by 5 delta O plus 2p. Now what you have to do to find CFSE? E ligand field minus E isotropic field, right? So ligand field minus isotropic field. So this minus this, effectively you get minus 4 by 5 delta O, right? If you use this method, I am telling you, you will never make a mistake in calculating CFSE. You can take the case of D7 low spin. In this case, D7 again, but low spin. So E isotropic field is same, 7 into 0 plus 2p. However, in this case, T2G sat is occupying 6 electrons, while EG is having only 1. So minus 0.4 into 6 plus 0.6 into 1. And how many p pairing energy? 3 orbitals are having paired spin. So here it is 3p, right? So that is how you calculate 6 into minus 2.5 delta O plus 1 into 3.5 plus 3p. So you get this value, minus 9 by 5 delta O, okay, or minus 1.8 delta O plus 3p. So if you from this minus 1.8 delta O plus 3p minus 2p, 2p is the energy in the isotropic field, you get minus 9.5 delta O or minus 1.8 delta O plus p. That is the effective CFSE, crystal field stabilization energy in this case. All right. Use this method, you will never make a mistake. Okay, you can find there are various tables of crystal field stabilization energy, so you can calculate wherever there is more. Okay, a compound is expected to be more stable. Okay, compound is expected to be more stable. Like you say, D0 case, no CFSC. D5 high spin case, high spin. Where is the high spin case? High spin, this is over here, zero CFSC. D10, everything paired up, again zero. Only there is plus 5p, 5 pairing energy is there. Okay, but D0, D5, and D10 are having effectively no CFSC, right? So in these cases, properties are different, right, from the other complexes where there is some net CFSC is there. Okay, so CFSC, if you are considering, then you can see that only D0, D5, D10, okay, especially in case of the the high spin or D10 low spin, it is just the this CFSC you can consider as, okay, D5 low spin you have CFSC, okay, only D1, D0 and D5 high spin they are having net zero CFSC. Every other case there will be always something will be there, some CFSC will be there. All right. So that's why whenever there is no CFSC, so the stabilization factor will not be there. It will be same as if the compound complex is not formed. All right. Again, there are some calculations of CFSC in various cases. You can have a look at these values. This will give you an idea about which compound is expected to be more stable, which compound is expected to be less stable. Okay. So we will continue the discussion of crystal field theory and its applications in the next class also. And as of uh, as of today, we have understood a lot of properties by considering the splitting of the d orbitals in the crystal field theory. So our today's discussion we will be ending over here, and we will be checking some other applications of crystal field theory in our next class. So thank you.